All right, we're now starting to put some of the properties of sequences together so that we are guaranteed convergence of particular sequences. We will now utilize a theorem that we're going to accept without proof. That if you can show two things, one, that a sequence is bounded, two, that it's monotonic, then you can conclude that sequence converges. You may not know what it converges to, but you can prove it's going to converge. The two examples we'll look at are very similar sequences, A sub n and B sub n, and just so that we can get a real hang of it. And in our textbook, Briggs and Cochrane, figure 8.12 shows a picture of what's going on with these two sequences. So we'll first look at sequence A sub n. When n is 1, the output of the sequence is 2. When n is 2, we get 3 halves. When n is 3, we get 4 thirds. And 5 fourths. And I'm getting myself confused, aren't I? And when n is 5, we get 6 fifths, 7 sixths, and so on. So the numerator is always 1 bigger than the denominator. The output is always a little bit bigger than 1. And from the graph, we can see all these red outputs are between 2 and 1, and they're decreasing. In the second example, we'll show that these black outputs are between 0 and 1 and are increasing. And in both instances, we're going to be able to conclude from the bounded monotonic theorem that the sequences are convergent. Let's start with number 1. Okay, so we'll start with the bounded part. That's the trickier part. We need to show that sequence A sub n is bounded. And from the picture, we think we can show that each term in the sequence is maybe not strictly between, but between 1 and 2. Okay. So we need to show that each term, 1 plus 1 plus n, is between 1 and 2. Okay. And this gives us a little guidance of what we need to show algebraically. 1, it looks like we can show the term is adding a little bit more to 1 each time, so it should be pretty straightforward to show that that's bigger than 1. And then 2, the second thing, it looks like we need to be able to show that 1 over n is never quite as big as 1, so that the sum is less than 2. Okay. All right, so let's start with this black part. That's pretty straightforward. 1 over n is positive because n is positive. And then if that statement is true, we should be able to add 1 to both sides, write down the result. And so our first inequality is definitely true. This is more restrictive, this is less restrictive. Okay. Now we need to show that 1 over n is actually less than 1, so we'll probably start with our assumption, since n is an index for a sequence, n is greater than or equal to 1. So that's just kind of a fact we can start with. And so the reciprocal of n is less than or equal to 1. And again, adding a positive value to both sides, we get our second inequality. So putting those two statements together, 1 is less than each term, and each term is less than or equal to 2. So A sub n is bounded. Okay, so that's the first thing we needed for our theorem. We've shown boundedness. Now we need to show monotonicity of our first sequence. Okay, we usually do that with the derivative. Now we need to show monotonicity monotonicity. And so we'll take the derivative of the related function. And we've got the, let's see, the derivative of the constant will be 0. So we really need to just take the derivative of this reciprocal function, which can be written as a power. And what do we get? Negative x to the negative 2, or negative 1 over x squared. Ooh, that's straightforward. The denominator is always positive, the numerator is negative, the derivative is negative always for all x. Therefore, 1 plus 1 over n, the sequence is decreasing. And so by the theorem, the first sequence converges. We have an idea of to what it converges, but all we've proved now is that it does converge. So that's the first example. You might want to pause it here and see if you can prove example 2 converges. Can you find the double inequality that would show that it's bounded? By the way, some people would write, if a sub n is between 1 and 2, then the absolute value of a sub n is less than or equal to 2, and show that our function's bounded that way. But I'll leave it there. Okay. Did you want to pause and look at example 2? Okay. We had looked at the picture, the graph. 1 minus 1 over n are our terms. When n is 1, we get 0 as an output. And it looks like all these black dots are between 0 and 1. So we need to show that each term of b sub n is between 0 and 1. And we don't have to be so strict. We can let them be equal. Okay. Can we show our terms are positive? Well, we already knew that n was greater than or equal to 1, so the reciprocal was less than or equal to 1. And if we negate that, we turn the inequality around. And if we add a positive number to both sides, like adding positive 1, then we keep the relation like it is. So because our indexes are all greater than 1, we can show that each term is positive. So that was the first part of the double inequality. Well, at the same time, like we did before, our index is positive, so its reciprocal is positive. And if we negate that, we have to flip around the inequality. Now add 1 to both sides, and we show that our difference, our terms, are also less than 1. So putting that all together, 1 minus 1 over n is bounded by 0 and 1. Some people would say then the absolute value of b sub n is less than 1. A quick derivative, so also the derivative of 1 minus 1 over x would be the same as the derivative of opposite x to the negative 1, because the derivative of 1 is 0. And we bring down the negative 1, making this positive 1x to the, negative 2, or 1 over x squared, which is positive. Therefore, our sequence is increasing, and furthermore, again, right, we've got boundedness, monotonicity, therefore the sequence is convergent by our theorem. Okay, so in summary, if one way to show that any sequence is, well, not any, one way to show that certain sequences are convergent is to show two things. One, there exists a number, well, that each term is bounded, and two, that the sequence itself is monotone. Okay. Good luck with that.